In this video, we're going to discuss the use of cyclic acetals and also thioacetals. So cyclic acetals are pretty cool. They're often used as protecting groups, and they are created using a diol as the alcohol, which creates the cyclic portion of the acetal. So for example, if you take a ketone and react it with ethylene glycol, which is this compound here, you end up creating a cyclic acetal. So notice this still has all the features of an acetal. We've traded out the carbonyl oxygen, which is over here, for two alcohol oxygens. The difference here is that the two equivalents of the alcohol are actually attached to each other, and they're part of the same molecule. So that creates the cyclic structure. Now this is also reversible, just like any acetal formation, which is what makes these such valuable protecting groups. So remember, one of the things that we said about the formation of acetals is that they can be formed in acid, but they cannot be formed in base, and they also cannot be broken in base. So these are a perfect protecting group for an aldehyde or a ketone in the situation where you need to do a reaction with base, where the aldehyde or ketone may be susceptible to unfavorable reactions. So here's a perfect example. We have a ketone and an ester in the same molecule, and somehow we want to turn the ester into an alcohol without affecting the ketone. So the only way that we know to react or to reduce an ester into a primary alcohol is using lithium aluminum hydride. But if we use lithium aluminum hydride to create that primary alcohol, it would also reduce our ketone into a secondary alcohol. So we cannot simply react with lithium aluminum hydride and get the product that we want, because we would also lose the ketone. So this is a perfect setup for a protecting group. We want something that will protect the ketone but not the ester. So in this case, what we want to do is react with ethylene glycol in acid, and this will give us a cyclic acetal. From here, we can react with lithium aluminum hydride, and we don't need to worry about the acetal because these are basic conditions and acetals are base stable, meaning they will not react in basic conditions. And when we do this, we end up with an alkoxide formed from the ester, and our acetal is still present. Now, I didn't immediately draw out the aqueous acid workup here because the aqueous acid workup would also do us the favor of removing the cyclic acetal. So I wanted to draw that out separately. But if you wanted, you could go from our second structure to our final structure by writing these conditions out sequentially. You just have to remember that when you introduce the aqueous acid, not only is it going to protonate your alcohol, or your alkoxide to make the alcohol, but it will also get rid of your cyclic acetal. Thioacetals are acetals made from reaction of an aldehyde and a diol instead of an alcohol. So you take an aldehyde, react it with a diol in acid, we're just using generic HA here, you would end up with a thioacetal and water as your side product. So this reaction is completely analogous to the reaction to form an acetal, just with a diol instead of an alcohol, which makes a lot of sense. If you think about the periodic table, you have oxygen, and then underneath that you have sulfur. I guess we could fill it all the way in if we really wanted to. But anyway, so you often see similar reactivity between elements that are in the same group. So this is an example of that. You can also do this with ketones, and you can do this with a dithiol instead of a just regular thiol. So this is also, again, analogous to creating a cyclic acetal. We're just creating a cyclic thioacetal this time. And also, instead of using an acid, you can use a Lewis acid as your catalyst, and you would still end up with the same effect. So this brings us to some kind of neat chemistry. You can remove a carbonyl using this chemistry. So you take your ketone or aldehyde and you react it with a dithiol and in the presence of boron trifluoride, and you end up with your cyclic thioacetal. You can follow that up with hydrogen and what's called rainy nickel. This process is called desulfurization, and it actually completely removes the dithiol and replaces it with hydrogen. So we're not even just removing the thioacetal and getting our carbonyl back. We are completely destroying the carbonyl and turning it into just an alkane. So this is also doable, through something like Clemenson or Wolff-Kishner. So this isn't like really new. You've learned other processes to do this, but sometimes Clemenson or Wolff-Kishner conditions are not reasonable for your reaction. Oops, Wolff. So this is an example of an alternate pathway that you could take if you needed to get rid of a carbonyl without using, a mercury and zinc amalgam or hydrazine and base.